and been making your flashcards at least, uh, making them for the reactions that we've discussed. Because I'm telling you, this stuff is, you're gonna see this stuff so many more times, especially when we get to part two. And all the arrow pushing is like of the utmost importance. Like if that's still stumping you, then that's gonna be, you're gonna have a problem with part two, because part two is a lot of mechanisms and it's a lot of stuff that we already talked about. Dipoles and electrophiles and nucleophiles. That's why I spent so much time on that. So let's jump in to, where are we on here? We went through the mechanisms for, and I cleaned this up before I posted it Wednesday. So hopefully you got that and caught that I, because it was kind of jumbled up before. So I just tried to clean that up before I posted it. Yeah, so this is a fun part right here. And then we're gonna work through some of these other we're gonna skip this one because that's degrees on saturation. So we don't have to do that twice. We'll skip that. So here we're just predicting reagents, right? And figuring out what it would take to get to the product that's shown. And so with this, I'm going to talk about the Simmons Smith is not on here. So I'm probably not going to worry about that reaction. It's in the video if you watch the last video that I sent. And then the ozonolysis, I'm going to talk about that. And I'll try to make that as plain as possible because I know that mechanism in the video was quite involved with ozonolysis. So we're going to go right here. We're going to start up top. And we're going to do this epoxide opening. We're going to talk about that as well. Do y'all want to do that first, or you rather do start down here? I think we can come back to the epoxide opening. Let me see if there's an epoxidation down here. No. We can come back to that because that's an actual mechanism that we're going to have to work through. And I'll just add a page in, and we'll work through that. It's a simple mechanism, but I'll explain like when the epoxides get opened up, like what the conditions dictate. If you saw that video, then I think it should have been in there, but we're gonna talk about it still. All right, let's go down here. So it says identify reagents that you would use to accomplish each of the following transformations. So now this is kind of like, okay, I have the product, but what did I use to get to the product? So I have circled or highlighted, outlined in red, the three products that we care about. All right. And one of them, let's start with the diol over here. What would I add to this alkene? This is my alkene. Let me pick a different color. And we've been talking about reactions of alkenes. What would I add to this alkene to convert it into a diol? Right? Keep in mind, we've only talked about a certain number of methods. So nothing outside of the scope of what we've talked about, even though there are other methods, I don't care about those. We're only talking about the methods that we've learned so far. What set of reagents do we know of that I can add to an alkene and make it into a diol?
Osmium tetraoxide.
Good, excellent. Osmium tetroxide, right? So the reaction is what we call osmolation. And the reagents are 1, osmium tetroxide, OSO4, and then 2, sodium hydrogen sulfite. Is that right? That was on your flashcard?
Yes.
All right, good. That's what should be on your flashcard. And then somewhere on that flashcard, you need to put diol synthesis, because that's what osmium tetroxide does. It converts alkenes into diols. Diol, di meaning two, all meaning alcohol. All right. Questions about that one? And I think that was you, Sanaya, that asked about how the cyclic osmium intermediate gets broken up. I think, if I'm not mistaken, it just gets protonated. I don't think there's a really involved because I went and actually hunted that down um, to see like what the proposed mechanism was for that, and it's actually I think it just gets protonated, and then you end up with a osmium species that's not OSO4, but I think it's osmium dioxide as a side product because both of those oxygens from osmium get transferred to the alkene. So I think it just gets protonated and you just break the osmium oxygen bond. All right, let's look at the top structure. What first of all, what functional group is that up top? What did we convert the alkene to? Going from the alkene to that top functional group. What is that functional group?
An alcohol.
Very good. Alcohol synthesis. So this is, excuse me, an alcohol synthesis. Right? What tools do we have in our toolbox to convert an alkene to an alcohol? Because we talked about two reactions that we can use for that. Because osmolation, those are alcohols too, but that's a diol. It's not a single alcohol. So we're not going to use that. We got other tools, right? What tools do we have in our toolbox to convert alkenes to alcohols?
Oxymercuration.
Okay, good. That's one of them. Excellent. And what's the other one?
Hydroboration.
Good. All right, now look at that alcohol and where it's located. Now we need to think about the regiochemistry. You see which carbon, so here's my alkene. It's got two carbons in it. It's got a carbon here and a carbon here. Which carbon is that alcohol on in the product?
The least substituted.
The least substituted carbon. So which one of those two tools gives me that regiochemistry? And that's so that would be considered what? Anti or carbon to carbon. Is that right?
Yes.
Yeah.
So
That's
which say again?
It's hydroboration.
Hydroboration followed by oxidation. So this is hydroboration, oxidation. All right, so the first set of reagents is BH3. We're going to make that alkyl borane. Remember we talked about that on Wednesday, the alkyl borane, and this is done in THF as a solvent. And then the second step, hydrogen peroxide. I need a different color. Black. Followed by what? Sodium hydroxide. Right? That will give us anti or carbon to carbon addition of H and OH. Right? Questions about that one? Again, the regiochemistry gives it away. The fact that the OH is on the least substituted carbon in that alkene, that's a dead giveaway that in order to get from the alkene to the alcohol, we had to do hydroboration followed by oxidation. This is good. All right. Let's look at the next one. What do you think? What did I do to the alkene? Here are the two carbons, in case that the way it looks is confusing you. The two carbons in the alkene are here and here. Right? Is that right? So what did I add to those two carbons? Let me show you. Let me write this in too. This is a CH3. And then I added an H here. Oh, I'm sorry, not an H. My bad. BR. I added BR. All right. What do you think? What did I add? Looks like I added H to one carbon and BR to the other carbon. Is that right?
Yes.
Because this carbon here, since it's terminal, is actually a CH2. right? Remember that. That's the end of an alkene. And it hasn't have 4 bonds to it, doesn't have a charge, it doesn't have any, it's not a radical, it's not a cation, an anion. So it's got to just be simple CH2. So I added H to one side, Br to the other side. What's my reagents for that? Y'all should be tripping over each other to answer this question.
Is it HBr?
HBr. Right? And that's addition of HX. That's the reaction. That's on the top of the flashcard. And the reagents for that is any halogen or halogenated acid, HBr, HCl, HI. Remember, HF won't work for that. It's not a good reagent for that, but chlorine, bromine, iodide will all add across that double bond. All right. This is not circle. Go ahead. This isn't circle. Well, it wasn't, but it is now with my crappy handwriting. How would you make that? First of all, what type of product is that?
It's a halohydrin product.
Come on, man. That's exactly who is that? Chester?
Taj.
Taj. Come on, Taj. It's a halo hydrogen. Very good. What reagents would you use for that?
Br2 and water.
Man, y'all just make me y'all just made my Friday. We're gonna use bromine and water. Excellent. And that's a halohydrin, right? The OH, you see where it is, opposite of the Br. And this is the giveaway, right? You got an OH here and a bromine here. So that's a halohydrin. Excellent. Excellent. All right, let's go to let's do this bottom example. In blue, highlighted in blue. And I want to do this one too. Let me highlight that one. And then we're going to step away from this page to talk about the ozonolysis. I'll do this one as well. All right. Somebody help me out with this one. With the don't let the stereochemistry freak you out. All right. If that methyl group is on a dash like that, all that means is that there's a hydrogen on a wedge right here. All right. So you can see what we did. We added H and OH to the same face. And it just so happens that OH is where? On the, these are my 2 alkene carbons right here. So where's the OH in relation to those 2 alkene carbons?
On the lead substituted.
Substitute a carbon. And it's an alcohol. So what's my set of reagents for that? Then we just do this up top.
Is it a hydroboration and oxidation?
Yes.
So BH3 times THF and THF, and then H2O2 and NaOH.
Yes. Excellent, excellent, excellent. All right. What about I know this is redundant. I shouldn't have done that other one that I circled. That's redundant. What about this one? You got an OH and a Br that got added across that double bond. Just like we had up here. Is that right? The only difference is the stereochemistry is showing. You see how the OH is wedged and the Br is on the dash? That means that they are what? Are they cis or trans?
Trans.
Trans to one another. right? This is going back into the page, the Br, and the OH is coming out of the page. That's what that stereochemistry indicates. So the fact that you have an alcohol and a bromide added across the alkene and they're trans, right? That's another, this is another example of halohydrogen synthesis. All right, so it's just gonna be Br2 and H2O. All right, what about this one up top? What did I do to that alkene? Give me one set of reagents one reaction that can take the alkene down to an alkane.
Hydrogenation.
Good, excellent. So hydrogenation. Right? How do I know that? Because the alkene, all I did was add a hydrogen to each side, right? And it converted into alkanes. So we talked about two methods for this. One method is, well, we know we got to use hydrogen gas, right? That's a given. But your catalyst can vary. There are actually lots and lots of catalysts for hydrogenation, but we've only talked about two. We talked about either platinum oxide or palladium on carbon, right? Either one of those would work to carry out this transformation. But the hydrogen gas is the key, right? Because that's where your hydrogen is going to come from. So platinum oxide, let me make sure that you don't think that 2 is a Z. Right, so platinum oxide or palladium on carbon with hydrogen gas. All right. So now I want to take, let me see if I can, I'm just going to redraw that. I want to take the ozonolysis and discuss that. So this is my alkene. Got too many carbons in there. All right, so this is an example of conversion of an alkene into a carbonyl. This is one way to do it. Right, there are other ways that are indirect. Right, we don't learn those reactions in part 1, but we can take a alkene and convert it to an alcohol and then oxidize the alcohol up to a carbonyl. But that's an indirect way. This is a direct way of converting an alkene into an alcohol. All right. And this is an example of what we call ozonolysis. Right. So the reagents, I'm just going to go ahead and give you those because we haven't talked about this. O3. So ozone, and then zinc and acetic acid. So when you see HOAC like that, that's the OH part, the hydroxyl part of the carboxylic acid, and this is the AC part. So we call it acetic acid. So HO is here, and then AC is the carbonyl. All right, so don't get freaked out when you see that. So it's ozone followed by zinc and acetic acid. And this is a very complicated mechanism. I'll be the first to say that. I'm actually going to pull up the PowerPoint and with the structures on it so we can go through it. But let me give you a generic example. All right, so if I have an alkene like this, right, and I treat that with ozone, the most basic way to think about this is to think about the alkene being cracked in half, right? So I'm going to crack this in half, right down the middle. And each carbon in that alkene is going to become a carbonyl. So if this is my alkene, I'll get two products from that. I'll get this and I'll get this. All right. Anybody not see that? I'm going to pull up the slide because that mechanism is long. I'm just going to walk you through it, but I'll pull up slide for that and walk
Oh,
through it.
I don't see it.
Go ahead. What's the problem? So
Like, how did you separate? Like,
I'll have to, I'm gonna show the mechanism to show how the actual alkene gets separated, right? But there's an intermediate what we call a malosonide. So in this case, it would look like this. So this is the intermediate. Right. So you can see right here, this is where my oxygens are gonna come from. All right. So I end up breaking this bond, right, in that malosonide, and I end up breaking this bond as well, right? So you can kind of see where it's going to come from, right? But the key is that you're adding oxygen to each, you're adding oxygen to each one of those carbons. And so that's how they both become carbonyls. I'm gonna pull a slide up so I can make sure that we go through and look at each part of that mechanism. But yeah, so think about the alkene itself. Remember that it's composed of two carbons. So you got a carbon on this side and a carbon on this side. So even if you don't know how it happens, when you see O3 in the presence of an alkene, just know that both carbons in that alkene are going to get oxidized up to a carbonyl. Let me show you why this one looks like this, right? Because if I break this double bond here, like so, right? I'm not touching any of the other carbons in the chain or in the ring. So all that stuff stays intact. And so when I crack that double bond in half, that's how I end up with, and let me highlight the two carbons where the carbonyls are. So this is one of your alkene carbons, and this is the other one, right? So in the product, you can see that one of those carbonyl carbons, let me make sure I got enough carbon. 1, 2, 3, 4, 5, 6. Yeah, that's enough. One of your carbonyl carbons right here. That's the, I'm sorry, not that one, this one. That's your aldehyde because this has a H on it. Let me show you that. So there's a hydrogen there, same hydrogen right here. And then there's a CH3 group here. And that's the same CH3 here. Right. So those two carbons are the carbons that get converted into carbonyls. Right. So it doesn't matter if it's cyclic or if it's acyclic. If your alkene is, you can still do ozonolysis on it. So this is cyclic, right? That means that it's a ring, right? So let me see what this is. One. So this is 1-methyl cyclohexene. I don't know if you recall, that's not going to look like good when I post that. I don't know if you recall when we talked about alkenes, or cycloalkenes. I think we did some nomenclature on one of them before. And we talked about how you name it, right? So, and we said that alkene, the double bond is always 1 and 2. So in this case, because this carbon is substituted with a methyl, we're going to start there. So that's 1, and that's 2, 3, 4, 5, and 6. Right. So the hex, that means it's 6 carbons. Come on, Russell, tighten up. The ene means it's an alkene. The cyclo means it's a ring, a 6-member, well, a ring with 6 carbons in it. And then the 1-methyl just means that there's a methyl group on the first carbon. And anytime you have a cycloalkene like this one, then the double bond in the ring is you're going to start counting there, 1 and 2. Right. So this is an example of a cycloalkene. Cyclo meaning ring, alkene meaning there's a double bond present. All right. So whether it's cyclic or acyclic, it doesn't matter. If I treat this under ozonolysis conditions, then I'm going to convert each carbon in that double bond to a carbonyl. Sometimes if it helps, like I know this is kind of a crude way to think about it, but if I break that double bond, if I know I'm going to break the double bond in half, sometimes it might help you just to write in an oxygen here and an oxygen here. That way you know that it's going to be a carbonyl, right? And it's not, and the double bond is split in half, right? I've shown that as an example of a way to think about it. Also, with the acyclic ones, I've also shown it, like if you take that alkene, if you think about this in a very rudimentary way, take the alkene and crack it over your knee. I think that said something like that in the video, right? Like taking a stick and breaking it in half, and each half of that stick is going to be one of the carbons in your alkene. So let me pull up the PowerPoint for this right quick. So I'm gonna pause recording. So
I have a question.
fine. Go right ahead. All right, so this is not cyclic, but it's the same reaction, and it's gonna go through the same mechanism. So you got an alkene here. These are your reagents, ozone, and notice the temperature, -78. That's very important. Ozone is they make ozonizers now that are really small and more safe. When I was a grad student, the ozonizer was, oh my gosh, it was huge, it was loud, and you had to put a blast shield in front of it because ozone is an explosive version. Because what you're doing is pumping in oxygen and then converting it into ozone so that it can be used to add to the alkene, right? And it's the same ozone that's in the ozone layer. That's the same compound, right? So, and then it's zinc and acetic acid, and then in the second step. So you're gonna break the double bond. You can see that gets cleaved, and then you're gonna get each carbon in the double bond here. It is now gonna be a carbonyl. It's gonna be double bonded to oxygen. All right, so the mechanism is here, right? So you got your O3 is going to add here, and you end up with a malozonide. So the ozone is going to add across the double bond, and you end up here with this malozonide. And then that part is what breaks down. So you get a fragmentation. You can see the arrows in there. So this is going to fragment like so. And then you end up with 2 fragments that look like this. And then they recombine, right, to give you this intermediate. And then when you add in zinc metal is a 1 electron donor. So it can donate 1 electron in this particular case. And it's going to cause this entire structure right here to rearrange, right? So that's how you end up with your double bond here between this oxygen. You're going to break this CO bond right here. You're going to break the OO bond right here. And you're going to end up with a double bond here between this carbon and this oxygen. And you also end up breaking this bond too. So, and then you end up with O2 and then then zinc oxide as well, right? So that particular mechanism, as involved as it is, the outcome never changes. If you have an alkene and you treat it with ozone, then that alkene is going to get converted into a carbonyl, right? And it's going to be either a ketone or an aldehyde. All right, any questions about that? All right.
Is this on Blackboard?
This handout, I mean, this
The
PowerPoint,
PowerPoint.
I can put it there. I'm not sure if it's there or not.
It's the same as the video.
Yeah, it's the same mechanism as shown in the video, but I'll be happy to upload the PowerPoint as well. No problem.
Okay, thank you.
So that alkene, treated it with ozone, and it broke that alkene in half, right? And each carbon in the alkene became a carbonyl. One side became an aldehyde, the other side became a ketone. All right, questions about this problem? And again, the chain in between the two carbons is there because fix that up. Right, the chain is there because those same carbons are over here. In the ring. And we don't break any, the only bonds that get broken are going to be the sigma and the pi bond that make up the alkene. That's it. Everything else stays intact. So that's why it's there's a chain between your two carbonyl functional groups. Right? If it was acyclic, like the one down here, then right, you're going to just get two products that are separate from one another. But if it's a ring, if we do ozonolysis on a ring, then it's going to end up like so. It'll be acyclic, but both carbonyls will be in the same molecule. All right, any questions about that? So now we know up here what reagents we can put. That was a long trek through the forest to get back to this, but so it's going to be O3, and then the second reagent, zinc, and acetic acid. All right. Time, we got what, 4 minutes left. Let's try to knock out this this example right here, epoxide opening. It's not too bad. I think we could do it and be done. So let me add that. Add a page into. Let's take this page out. All right. So this is an example of epoxide opening, right? And when you open an epoxide, you need a nucleophile to do so. So you're going to add a nucleophile to it. Right. So here, this is, and the conditions matter. You can open under either neutral conditions or acidic conditions. right? So under acidic conditions, it's going to open at the most substituted side. Under neutral conditions, it's going to open at the least substituted side. Right, so if we look back at our epoxide, you can see here that this carbon is more substituted than that one. And you can also see that there's sulfuric acid present. So this is going to be under acidic conditions. All right, so the way this happens, let me just show you real quick, and then we'll stop and we'll pick up on Monday. All right, so here's my epoxide. All right, so when I have this in the presence of an acid, I'm just going to put H plus. All right, it's that proton from the acid is going to end up on oxygen. You're going to do proton transfer with oxygen like that. Still got one pair of electrons and it's positive. Right, and so now my nucleophile is going to attack here at the most substituted site. There's a reason for that, right? If I ask you which one of those two carbons, keep in mind that these are CH3 groups. And then there's two hydrogens over here. If I ask you which one of those two carbons is more likely to be positive, which one would you say? The carbon that's substituted with the methyl groups, or the carbon that's substituted with hydrogens? All right, that carbon that's on the left side is tertiary. So this is more likely going to be more partially positive than the other carbon, right? And you can even think of a scenario where that bond actually breaks first before the nucleophile attacks, right? But when that happens, right, that carbon is more likely to be cationic on this side. So when when you have acidic conditions, right, that bond is going to be even more polarized when you do the proton transfer to oxygen, right? And so you're going to end up with this, where now that methoxy group is here. And that's positive. And then, sorry about that. You have an OH group here. And now you just need to do another proton transfer. And that's probably going to happen with the conjugate base from whatever acid. So that's just going to do this, right? And then you'll end up with your product. Right, but the key is that under acidic conditions, you're going to activate that most substituted side. It's going to be more activated. So the acidic conditions are going to activate the more substituted carbon. Right, that's why the nucleophile attacks there. And if you do it under neutral conditions, then it becomes more about sterics than electronics. So under neutral conditions, it's just going to attack the other side. All right, but we gotta, let me see. Yeah, we over time by 3 minutes. So we're gonna stop here. I'll leave that up. But I do need to stop recording. Are there any questions about the epoxide opening?